$10 I say that we have a lit quiz today.
I don't want to have a quiz on a little girl who had too many microphones.
You're welcome.
I don't care about you.
If you haven't, do take a quick look to make sure that quiz scores are not completely off. It is because I re-entered them by hand. There's no direct connection to our school. I entered them by hand, so it's often possible to transpose a number. If it happens in the 1st place or 10th place, it probably won't matter. But if it's in the 10th place, it'll make a big difference, right? So you want to talk about the difference from your previous score. And I tried to check this, but I had to do it all by hand. So there's a lot of scores to go through. The difference from your previous score should be, at absolute max 5 points, generally less than that. And more than that, that means I transpose the number and you need to tell me. So okay? I guess to transpose the right way, you still should tell me, but anyway.
Your mom. Come on.
Okay, I do not have your test grading. They take a long time. And I keep falling asleep. So,
I hear about this last week for nothing.
So far, they're going fine.
What do you mean? What's that supposed to mean?
So far,
you can't just say,
I don't, it's actually because of the complications of my grading system, this is partly intentional. I don't really have a good idea numerically what that means. Right, I just know that people, that like overall I see like some people, like most like, oh look, you're getting the fairly easy problems you're doing pretty well on, and the harder problems not so well on, and we just
all
like
the
that's sort of
problems
what I expect. They're going okay. Like there's nothing like, oh my gosh, how would you guys love this one bit. Oh, a little bit, the final second half is a little bit rough, but anyway. But we'll see. We'll see what happens. So I haven't finished grading, so we'll see what happens with the rest of it, right? But like so far, yeah. An interesting wave function some of you picked, by the way, for your grade. Some of them are remarkably precise. Like very, very detailed probabilities you gave me for your grades. I'm not sure how much time you spent put into that, but whatever. Okay. The other reason I didn't have an incentive to finish your test because I totally didn't want to go over your test today anyway. We're in the middle of the story and I want to finish it. It's a good story. Well, it's a good story unless you're Japanese, right? So the story is a story about uranium-235 and how to refine it. So remember last time we introduced that the reproductive factor K. You remember K? What was K equal to the calculator?
Less than 1.
What was it?
Oh, the amount of neutrons.
It's the number of neutrons what?
That you produce.
Good. Number of neutrons produced over what?
The number of neutrons.
Good. The number of neutrons produced over the number of neutrons in. Okay. You all right?
I totally don't remember.
Okay, that's good. That's okay. Not testing you, right? It's all fine. So then K equals 1, remember, is the critical point. Now, what do you really need to get K equal to 1? You definitely need the uranium refined so that you have enough of it. So there's enough percentage of U-235. The other thing you need is what? To make sure that you actually have a critical amount. What do you think? What do you say? You need enough of it because otherwise you run out too quickly, right? So what happens is there's a fission that happens. What really happens is not so simple, right? What really happens is a fission happens. It sprays like 20 neutrons out, okay? But maybe only 1 or 2 of them actually hit the uranium-235 nucleus because there's a lot of other uranium around, a lot of other things that can happen. Sometimes neutrons are too fast, sometimes they're too slow, and so forth. So a bunch of neutrons spray out, some of them hit, some of them don't. And you need to make sure there is enough uranium-235 around so that it can hit it. So it's not just about percentage, it's also about the total amount needed. If you don't have enough of this stuff, then there isn't enough, there aren't enough atoms to really trigger the reaction. You need enough atoms so you can keep going. So that amount is called a Critical mass, right? You need a certain critical mass of uranium. People often use that word differently now, but a critical mass actually means the amount of mass you need to be able to go critical, right? Now, mass is not the only thing that matters. The environment you're in matters. The density certainly matters. There's other things that can do it. But a critical mass is a shorthand. For uranium, critical mass is substantial. It's like, what's the number, like 25 kilograms, 30 kilograms, something like that. Which for uranium is not that big. It's very dense stuff, right? Yeah?
Are we like close to running out of production?
Uranium?
Yeah.
We still got a good amount of uranium. We're not in any kind of danger zone. They're not going to shut down the power plants anytime soon. It's not a limitless resource. I'm not sure actually where it is compared to oil. The estimates I've heard, people's estimates on these things tend to be politically motivated, and so they're often not the most reliable estimates, but the ones I've heard say 50 to 100 years worth left. So we're decent on it. You don't have to worry about it, your kids maybe. The fun part is not K equals 1, of course, even though that's the useful part. So inside the reactors in Mars, Illinois is inside one of the big reactors. I know, right? And in the reactors on Mars, they keep it at K equals 1. They use neutron rods, regulator neutron rods, to keep K exactly at 1. That was the feedback loop. But something interesting happens in the case when K is greater than 1. K is greater than 1 is very different from K equals 1. We refer to this as supercritical. Let's consider what happens when you pass criticality substantially. For example, for a simple example, let's just take K equals 2. K equals 2 means what? You send in a neutron, and how many neutrons come out? 2. And then from those neutrons, how many neutrons come out? 4, because each of them breeds 2 more neutrons, right? And then from the next one, you'll get 8, and then 16, and then what do you call this kind of growth? This is exponential growth. A lot you guys use the word too easily, but this is actually exponential growth. It doubles every period of time. Every so often, it doubles. Now, what do we know about exponential growth? It's very, very fast. It starts out 2, 4, 8, 16, right? And then after a little bit, it's already in the billions, a little bit more, it's in the quadrillions, a little bit more, it goes really fast, right? And so exponential growth is extremely fast. K greater than 1 gives you exponential growth in the number of reactions that occur. So, of course, we are talking neutrons going between atoms, so the amount of time these things take is not very large. And so, what does it mean if you can get a good supercriticality going? It means you can get more or less all of the uranium to fission, basically, at once. And thus release, say, a year's worth of nuclear power to power Chicago, but do it in half a second.
Wow.
And if you do that, what happens?
Meltdown.
It blows up, right. And so this, of course, is what people started with. This was a completely incidental side effect, because it was warm. And so the idea of going supercritical is that you can release all the energy at once, and that's a lot of energy. 0.25% of all the mass energy in a block of uranium released at one time, which comes out to a very large amount of energy. Now, doing this is hard because you can't just take half a critical mass here and half a critical mass here and then put them next to each other. What will happen if you do that? Well, what happens is, remember, these things happen fast, right? Well, you have 2 blocks of uranium. The parts that are closest to each other will go critical first. And what happens when they go critical? They don't quite explode, but they release a lot of, in the form of kinetic energy, which we observe as heat. It's primarily heat. And what happens when things get very hot?
They melt.
They shake. What do very hot things do? Come on,
Melt.
They burn. Yeah, they do actually. They expand. Thank you. They do burn too. You're right. Well, they expand first, and so when you start to bring them together, the reaction starts, and then the heat expands, and what happens? It pushes everything else apart, right? So once any kind of explosion starts, the rest of it gets forced away, and those parts don't go critical. And so if you tried to do it by just putting two things next to each other, you would release enough gamma rays to kill yourself. But you would not kill anyone else unless they were also nearby. And it would be a small explosion, probably not even a real explosion. Probably just get hot and then stop. And then, like I said, the burst of gamma rays would probably be enough to kill you if you were next to it. But that's your fault for walking around with critical mass of uranium, right? But it wouldn't cause an explosion. Okay, to get the explosion, you have to make this work all at once. You have to get it to explode quickly before it has a chance to blow away all the other fissile material. And so, when they started working on this, so you know the story behind this, right? Leo Szilard figures this out as credited of first figuring out this idea, but he's not the only one who comes up with it. He and a bunch of concerned allied physicists get together. Remember, this includes a lot of German Jews who are no longer German. They get together, they say, we think this is a big problem, and the big impetus from it comes from the person who really gets it going is which physicist? Albert Einstein. Albert Einstein writes a letter. Albert Einstein is perhaps the only physicist with enough international prestige that he can actually convince the President of the United States. Albert Einstein writes a letter to Franklin Roosevelt saying, this is a big deal, research this bomb before the Germans get it, because they can figure this out too. Roosevelt gets it, agrees, and puts a military general, Rose, in charge, paired with a physicist, Richard Oppenheimer, who together start what is called the Manhattan Project, which you'll notice has nothing to do with Manhattan. It was just a name. The Manhattan Project took place in which state? New Mexico. Right. Los Alamos, New Mexico, where there is still a top secret nuclear base in Los Alamos, New Mexico. The same the lab's still there. And they still do nuclear research there.
Why was it called the Manhattan Project?
Because they wanted to give it a misleading name.
Yes.
It's exactly the reason. They wanted a name that had nothing to do with what actually they were doing. And it worked.
It's like when they broadcast white static in the Cold War, so that Russia would spend all of its money trying to decode nothing.
Right, decode static, yeah, exactly. We have a lot of strategies like that.
We're going to talk about Richard
Strategies are really interesting. Anyway, so they start working on this thing, and they figure out pretty fast that it's actually not that hard to do. In fact, the design was so simple that they never tested it. The first, it was never done. They never did a test run. It was the first time it was attempted was in an actual wartime situation. But it works like this: you take a critical mass of uranium and take a piece out of it, so it's not quite critical. You take that piece and you put it over here, and you put it inside a gun. It's not literally like this, but it's basically a long gun.
Can I take a picture?
Why do you put it inside a gun? What does it do? When you're ready to fire it, when you detonate it, right, it just fires the gun, which makes this thing go very fast right into the center. Because it's going so fast, it slams into the center while the fission reactions are just starting. And so that goes fast enough that it can trigger criticality in the whole mass of uranium, more or less all at once. You get, I forget what the yield is, like what percentage of the uranium fissions, but it's a good chunk of it. Now, to get this to work, you do not work with reactor-grade uranium. This is important for understanding how the world works now. Reactor-grade uranium is useless for this sort of thing. If you try it, nothing will happen. It'll heat up slightly, and that's it. You have to do it with what's called highly enriched uranium. Highly enriched uranium is over 90% U-235. Okay? Extraordinarily expensive stuff, and among the most dangerous stuff on the planet, because this is all it takes. And you know what? It's not that hard to build a gun. And so it's remarkably easy to build a gun out of uranium-235. When they first worked on this, they asked the Navy, hey, we're not going to tell you anything else about what we're working on, but we have a payload this big that we want to go at this velocity. How big a gun do we need? And the Navy said, oh, you need a gun that is 6 feet long. So they designed a 6 foot, gun barrel, right, with gunpowder at the other end. And what would this bomb look like? It would be a long, thin, 6 foot long thing, right? Okay. Then after a while, they realized that when the Navy does their calculations, they probably assume you're going to fire the gun more than once. This gun is not firing more than once. And so if the explosive gases from the gunpowder and stuff rip the gun apart, that's not a big deal, as long as the bullet flies straight. As a result, it doesn't have to be that long a gun. The acceleration can happen faster. And so they're able to condense it from a 6-foot gun to a 3-foot gun.
Wow.
And the result is a very powerful bomb that is this big, right, and narrow too. So this is the original design for a fission bomb, and is still kind of unfortunately the easiest design of a bomb that we can come up with. And all you need is a large chunk of highly enriched uranium. Good news is, highly enriched uranium, as we discussed, is very, very hard to make, right? So because of how difficult it is to make, they figured this part out early, and then they waited around 2 years to generate enough uranium, right? Well, I talked about all the plants at Oak Ridge. So while that's going on, they needed a plan B in case that didn't work out. So the plan B was working off another fact, which is most uranium is what isotope? 238. Okay. So if you add a neutron to uranium, neutron plus uranium-238, what do you get? Okay, uranium-239. Uranium-239 is a beta emitter. It undergoes beta decay. What happens when you undergo beta decay? What changes? One neutron turns into a proton. A neutron decays into a proton, right? So this neutron decays into a proton. That means it will change atomic number up 1, right? It gains 1 proton. So what's one atomic number higher than uranium? Neptunium. Get it? Uranium, Neptunium. This becomes Neptunium-239, which is also a beta emitter. And it's a beta emitter. It will then decay to plutonium. You get it? Uranium, Neptunium, plutonium. So plutonium is an alpha emitter, and it's relatively stable. These are, this one's like seconds, this one's like days in half-life. But this is a much longer half-life, okay? Plutonium is the first man-made element made in any sizable quantity, that's like mass-produced, and still the only one we really spend a lot of time on. Making elements is not easy, and plutonium is the only one that's really useful. Well, there's a few other ones. Californium has its uses, for example. Turns out. Einsteinium, sadly, pretty much useless. So plutonium is a remarkable substance. It is probably the nastiest stuff. It's the nastiest element on Earth. Like we can make deadly compounds and stuff, but as far as just raw elements go, it's really nasty. Plutonium is a very, very active alpha emitter. It's so active that a piece of plutonium is warm to the touch from the alpha decay, which is fine because it's all alphas. But plutonium also very easily forms a dust. It turns into a dust very easily, which is bad, because then it gets into your lungs and bombards your body from the inside, right? It is very, very fissile, extremely fissile, much more so than uranium-235, which is why we're interested in it. Because you see, if you just bombard regular 238 with protons, with neutrons, you'll get plutonium naturally. And where do you bombard regular uranium-238 with neutrons? In a nuclear reactor, where still most of the uranium is uranium-238. So as a byproduct of nuclear reactions, you generate plutonium. And plutonium is a different atomic number, which means a different orbitals, different energy levels, which means that you can chemically separate plutonium. It's much easier to separate plutonium than it is to separate U-235. You don't need a centrifuge, you just need a chemical process to get it out. So plutonium is therefore a lot easier to get because you can just start with regular uranium, not the crazy stuff, and just put it in a nuclear reactor and wait a few weeks, and now you have a chunk of plutonium, or partly plutonium, and then you can chemically separate that, and now you got your plutonium. Plutonium's critical mass is a lot lower. It's like half that of uranium-235. And it's much easier to make pure, and it's far more fissile. And so plutonium is a much better fuel than uranium, as far as that goes. It's not very good for nuclear reactors because it's too fissile. And it's very expensive to make, right? But if you're using it for weapons fuel, it's very important. The good/bad news about plutonium, depending how you look at it, is that the gun design does not work for plutonium. It's too fissile. As soon as the gun bullet gets anywhere near here, even if you fire it very fast, it starts to explode, and then it blows up, and it blows the bulk of this stuff away, and most of it will not fission. So plutonium is much more difficult to work with, and a large amount of the work they did at Los Alamos was trying to figure out how to get plutonium to work. The answer is something that, as far as we can tell, the North Koreans have still not quite figured out. It's very, very difficult, is why. So It's very, very difficult, and it's possible that it was only figured out once in America. We're not completely sure. Not everything. Not everything is clear, but it's possible that the details of this were stolen by both Russia, Soviet Union and China. It's not necessarily. I mean, smart people can figure stuff out, but it's also possible that it was stolen because it's really hard. But here's the idea: you take a piece of plutonium that is not quite critical. Actually, right in the middle of the plutonium, you need to put your neutron source, which is americium beryllium. Americium is an alpha emitter that hits the beryllium that knocks out neutrons. That's your neutron source. Okay. Then you put a piece of plutonium that is not quite critical, and you put it in a perfect sphere. And then around, well, okay, I can make it a little bit bigger than this. It's a good sized sphere, plutonium. Okay. And then around the plutonium, you put explosives. Incredibly carefully designed, shaped plastic explosives that had all the Navy's best munitions experts working on it to figure out how to make it, to time the explosions, and to detonate them in just the right way so that the explosion causes the combination of these things causes a spherical shock wave that's going inward. Okay? You have to basically build plastic explosives just right so that they don't blow up, they blow in. Right? And it has to be more or less a perfect sphere of explosion, which is hard to do, but it turns out possible. And so you get this explosion, and what's that explosion going to do to the plutonium? It's going to compress it. When it compresses the plutonium, which was not quite critical before, what's going to happen? It's going to go critical, and then the shock wave will hit the neutron source at the center. The neutron source kind of bursts open with all its neutrons, if you like. The neutrons go flying out into a now critical piece of plutonium, and it goes. Right. This is very hard to do, but far more effective. Yeah.
So like they don't know this model, or like it's just part
If
of
I know the model, I think they know the model. It's not like
It's
there would be a
that.
problem if they were otherwise. They definitely know the model. The one part. There's interestingly only one part of the Manhattan Project that is still classified today, and that is the details of the detonation of the explosives. It's still classified. You know why? Because North Korea can't do it. That's why it's classified. And a closely guarded secret, apparently very complex. It's still 40s technology, but hey, they can do a lot of things. You can do a lot of things. You put the resources of an entire country behind it, right? So this is how plutonium bomb works. So what would this one look like? What would the bomb look like? A big sphere. That's right. They put fins on it to stabilize it, and that's it. But they think basically it's a giant sphere. So they refer to this one as little boy and this one as fat man. This one was a lot more complicated, so they had to actually test it. It worked. So
It works. That's about it.
So does it detonate on impact?
and it's you use a regular conventional detonator, right? They were not impact; it was an altitude detonator. So when the air pressure drops to a certain point, then you are rising to a certain point, then it detonates.
Yeah,
So
none of
it's
the bombs.
far more
None of the bombs
effective
actually
than- You don't want all the energy going to the ground, right?
Yeah.
They knew all about that. We learned a lot about bombs and detonations in World War II. We were fine on that part, right? But the bomb itself was the tricky part, right? The first man-made nuclear explosion to ever occur was at Alamogordo, New Mexico. It was a plutonium bomb in a sphere design. They put it up at the top of a tower, and then they moved everyone several miles away. What I can gather from the accounts of people who were there is that the videos of the atomic bomb do not do it justice at all. Apparently, it is an utterly stunning, kind of ridiculously absurd sight. Brighter than noon, they say. They did it at night. So they said the whole sky becomes brighter than noon. And the fireball, they said, was multicolored. They talked about greens and purples, which for whatever reason don't seem to show up on any of the film footage we have. And of course the wave of heat and shock and stuff. Even when you're several miles away, is pretty remarkable. When they got to it's a desert, right? When they have a picture of Graves and Oppenheimer taking a picture next to the twisted remains of the tower, of the bottom of the tower, and the ground there has been fused into glass from the heat. So it's a powerful thing. And remember, this is now called a small nuclear device.
How is there like no follow, like there was
Also no radiation? Oh, there was.
Ugh.
Incidentally, Gross and Oppenheimer both died of cancer, and it's not impossible that
Walking out.
I mean, other people get cancer too, but anyway.
What's been
Let's talk
like?
for a
You
moment
just killed yourself.
about what happens when you detonate one of these things. What you really create is a huge amount of energy at one spot. Okay. What is the form of that energy, the primary form of that energy first? No, before heat. Before that, what was the original form of the energy? Gammas. Lots and lots of gammas. A lot of the gammas get converted to heat, but a lot of them don't. So naturally, the gamma rays come first, right? Because they go faster than anything else. So the first thing that always comes from a nuclear explosion, there's a lot of accounts we have from survivors that have been studied carefully. That everyone agrees, though, the first thing that comes is the flash. There's a very bright flash. That flash is very bright, but most of the energy is not visible. Most of it is the gamma ray spectrum. You're just seeing the low tail of it, and it's still very bright. It's a very bright flash that takes with it a ton of gamma rays that do their damage already, right? But the flash always precedes everything else. In fact, at a decent distance, there can be 10 seconds between for a larger bomb, 10 seconds between the flash and everything else. So the flash comes first, then what's left behind?
the shockwave.
Yeah, well, it's hot, right? That was the other thing we had, right? Most of it gets converted into heat. What do hot things do? Expand. Now, how hot is it? Would you believe that if I told you that it was as hot as the surface of the sun?
Yeah.
Well, it's not. It's actually hotter. It's as hot as the center of the sun.
Whoa.
Okay? It's extremely hot. So it's basically a small, tiny piece of the sun dropped on Earth. Okay? What does it do? What do hot things do? Expand. How quickly do they expand? Very quickly, thank you. So I'm glad we had this scientifically worked out. It expands very quickly. What happens when something expands very quickly? It's called a shock wave, right? They call it a shock wave, and the shock wave is extremely powerful because it's expanding very, very, very quickly. It's just hot air, but it's really, really hot air. Really hot plasma, but it's extremely hot. So it's so hot that it's basically impossible to stop. So the explosion from it pushes everything out of the way, which is why when you look at the footage of nuclear bombs, what you see is this very fake-looking, perfectly spherical or hemispherical shockwave coming out that goes like it looks like an old video game. And it gradually fades out. That's because eventually it cools off as it expands, right? The energy spread over a larger surface area, so it cools off as it expands. Eventually it gets cool enough that it drops below the visible spectrum, and you don't see it anymore. So what you see is what you get is a shockwave. That's the explosion part of the explosion. That's the damaging part. The shockwave is the part that will knock over all the buildings and stuff. It's so hot that it expands so fast that it's basically unstoppable. It just rips apart everything as it goes on. Eventually, the energy gets spread out more, and it will do less and less damage as it goes away from the epicenter, which is called, what do they call the center? Ground zero. What they call ground zero. So from there, that's less. Now, what's left behind once the shockwave passes through?
Bunch of radioactive.
Sadness.
But before the radioactivity, what did I say caused the shockwave? The fact that it was hot. What do hot things do again? Burn. That's right. So what's left behind is a lot of fire. You notice that in explosions, regular conventional explosions, you've seen them on movies. By the way, a good number of explosions in movies are not computer generated. They just blow things up. Which, I mean, yeah. There's a Jackie Chan movie, I forget which one, Police Story something, 4 or 2, I don't remember, where he runs out, at the end, he runs out of an exploding building that's about to blow up, and then it blows up behind him as he jumps out. They actually did that. Because he's Jackie Chan, he's crazy. So he runs out of the building, but they blow up the whole building. Because they totally just wanted to blow up the building, let's face it. Anyway, so when you see what they look like, those are real explosions. There's always lots of fire. That's because of all the energy, it catches things on fire, and so you get a lot of fire left behind, okay? That's where all the red color comes from. It's from fire. A lot of things burning. Now, when you have a whole lot of area burning at once, though, what does it do? What does hot air do?
gonna ask a question.
Oh, go ahead, next question.
Fire, as it heats up to a hotter temperature, it will emit different colors.
It's true, yes, and that's where the different colors apparently come from. They never seem to show up on the footage for whatever reason.
Is green fire common? Like what?
Common? No. But remember, a lot of things are burning besides carbon, right? Red is the regular carbon fire. There's a lot of other things burning, and different salts, as you know, that create different colors. You should know from chemistry, and so that might be part of it. I don't actually know much about that. But what does hot air do? It rises. So now you have a sudden appearance of a gigantic amount of hot air, like right at the surface. Above it is much cooler air, right?
Oh.
So what happens when you have hot air, cool air? Midwesterners? You basically get a tornado. It's not quite a tornado, but it has a lot of the same principles behind it. It more or less forms a fire tornado. In particular, rather than just rising uniformly, it picks the hottest points at the center and tends to suction everything up towards the center, like a tornado does, right? And so instead of just getting a general flame, you end up sucking all the flames up towards the center of it, where it creates a giant column of flame. The flame rises higher and higher in a straight column until eventually it gets cool enough that it no longer has that suction effect. It cools off as it rises. And once it gets high enough to reduce the suction effect, it just kind of disperses generally, creating a mushroom cloud. Right? The mushroom cloud is characteristic of any large explosion. Radioactivity has nothing to do with it. It's just a very large explosion. We can make it. We have a conventional bomb. They call it the MOAB, or mother of all bombs. We have a conventional bomb that uses no nuclear power that's bigger than the Hiroshima bomb, and it creates a mushroom cloud too. That is this characteristic mushroom cloud. It comes from the thermodynamics situation, very hot air suddenly forming all at once, getting sucked up into the higher atmosphere. Now, go ahead.
The radiation from a nuclear bomb can only travel a certain amount of distance, right?
Well,
That depends on a lot of things.
This depends on what you mean by the radiation. So the emitted radiation from that first gamma ray blast does a lot of damage, but it's only released all at once. And yes, of course, it disperses like anything else as the surface area increases. So that only goes a certain distance, then it's fine. But in the midst of all that burning stuff, there's something else left over from the nuclear bomb. What else was left over from the nuclear bomb?
Anything that was in the bomb didn't fission.
Right, well, I'm not so worried about the stuff that didn't fission, it's the stuff that did. What's left over is called fission fragments. Remember, when the uranium splits, it splits into two isotopes, kind of chosen randomly, and they're almost always, because they're chosen randomly, they're almost always radioactive. And so you end up with a whole bunch of radioactive dust. Now, remember, you cannot destroy atoms. We don't have the power for that, right? All of that ridiculous power was just to break them in half, right? And that's all we can do with it. The atoms themselves are not going anywhere. They can't get destroyed. So those things are still around. When that mushroom cloud effect happens, it sucks all that radioactive dust along with everything else up into the upper atmosphere where it finally cools. What does it do? It's in the upper atmosphere? It falls down. A lot of times, though, it first gets picked up by higher air currents, especially if you're near the jet stream. Do you guys know what the jet stream is? It's where jets fly. It's a big like current of air up in the upper atmosphere that moves around the Earth, called the jet stream. If it gets picked up in the jet stream, it will go wide in the distance because it's dust, right? But eventually, this stuff will fall, and when it falls, we call that fallout, right? Fallout is a problem because it is not the bomb anymore. It's the leftover radioactive fission fragments that are now being dispersed literally across the entire planet. Not evenly, but it does make it across the planet. Explosions in, say, Nevada can definitely fall out over the Pacific or in Africa or in Russia, and you can go anywhere. Depends on the winds and stuff. The fallout coming down, if it's fresh fallout, basically, in other words, the thing came out, this stuff is very highly radioactive and can still do some substantial damage to the area. Well, not explosive damage, right, but medical damage, because the stuff is very highly radioactive. After a while, the real bad stuff decays real fast, and the stuff that's left over remains in our water supply and our food supply, which is why, did you know, you are all more radioactive than your grandparents. They've done studies on it. You have more radioactive isotopes in your bones than your grandparents do. You can almost date someone by the radioactivity of their bones. I mean, date in terms of find how old they are, not the other kind of date. That would be a strange thing. One of the ones they talk about, it's interesting, they talk about it in terms of the amount of radioactivity is very small, but it accumulates. It's not good for you. And the amount of radioactivity is measured in sunshine units. That's what they use for it. Kind of interesting little Cold War spin on things. Isotopes that people are concerned about are things like strontium-90, which has a half-life of 30 years, which is basically short enough that it's pretty radioactive, like it releases quite a bit, but long enough that it hangs around a long time. So strontium-90 is one that people worry about. Cesium-133 is another one, 135, whichever one it is, one of those isotopes. Cesium is the one that they hand out the pills for. No, that's not cesium. That's iodine, of course. Iodine is the one they hand out the salt pills for because iodine in your body is focused in the thyroid. If you eat stuff that's been contaminated with radioactive iodine, it might not be so bad that all of it goes to your thyroid, which concentrates it, causing damage there. So what they do is, if there's in danger of this kind of fallout or something like the Fukushima incident, you take a bunch of iodized salts right away to pack up your thyroid full of iodine. Then it's like, oh, we don't need any more iodine, and you won't absorb it. That's the plan. Remember, it's chemically identical, so your body treats it exactly the same way, which is radioactive. Okay, let's talk a little bit about what radioactive particles do to your body. What do they do to your body? High energy particles shooting through your body. We know what they do in chunks of iron and scintillator. What do they do inside you? They come through things, right? Whatever they hit, they break. What do they break?
DNA.
Right. The biggest thing they break is DNA. What happens if they break DNA? Well, if you're lucky, it slices the DNA, and that renders that cell incapable of reproducing. Your body has a mechanism for recognizing that, and then it just destroys the cell and continues on its way. If you're unlucky, of course, it will trigger a mutation, which I guess the principle could give you spider powers, but more likely, will have negative effects. What's the primary negative effects of mutation? Cancer, right? Cancer is caused by an unfavorable mutation. So that's why radioactive materials are associated with higher cancer rates, because they increase the mutation rate and thus increase the release of the cancer-causing oncogens in your genes, right? The thing is, at the low levels, it's not really such a bad thing. I mean, increasing mutation rates is not good in general. That increases cancer rates. They don't like that. But it also increases the number of X-Men we have, so it's not so bad. But the thing is, almost all damage, your body can heal just fine, right? Like, we give you an X-ray, then it does do damage to your body. It slices apart some cells, slices some DNA up, and your body is like, take care of that, and then it destroys the cell and makes another one, right? Your body's good in that way. We are very good at recreating cells, and so it's not a big deal. We always take precautions, but it's really not a big deal to get an X-ray. Your body recovers right away. The big problem is, the big difference when you're talking about the gamma ray burst from a bomb is the acute radiation doses, they call it, meaning you get a lot of it at once, not spread over time. When you get a lot of it at once, it's the body is not capable of repairing all that at once, right? It's too much for the body to repair. And the thing is, radiation doses are always distributed across the body, right? They're never at one place like a wound. They're always spread out across the body, so basically you go through and you're going to kill 1 in every 100 cells at random, right? At that point, your problem is not mutations. Your problem is a lot of your cells have died everywhere in your body. And so what happens is, if the damage from the radiation is too great, your body is unable to repair itself. And so, because the repair facilities are also damaged, right? And so, gradually, over time, the organs in your body begin to stop working, because the cells are damaged and it's no longer able to keep up, and the production mechanisms are damaged, and all the things that make the cells are damaged, and so gradually your body begins to stop working. Over time, organs start to shut down. The ones that trigger first are the ones that need to reproduce fastest. So that's what cells in your body reproduce fastest? Skin. Come on, you guys know something about radioactivity. This is always associated with radioactivity. radioactivity-related cancer treatments, hair, right? And something inside you that's constantly being burned by your own body. Stomach lining, okay? Those are the ones that have to go fast. Hair, fingernails as well, they grow fast, right? The hair, skin, stomach lining, those are damaged first. Because they reproduce faster, they feel the effects faster. So hair falls out is one symptom of severe radiation sickness, and a lot of vomiting, vomiting blood and stuff like that, because the stomach lining is not able to keep up anymore. Then over time, the other organs stop working. So slowly, other organs are incapable of working. Your body is very good. Your brain is almost never affected because it's extremely well protected. But your body always prioritizes major vital organs. But eventually, the kidneys start to shut down, the liver starts to shut down. It just can't keep up anymore, and the organ itself starts to die because the body's unable to supply to repair all the parts that are broken. And remember, it's not like something you can remove by surgery. It's spread out through everything, right? And so gradually everything begins to shut down, and your body is unable to keep the blood clean, the body is unable to remove toxins, the body is unable to process nutrition, and eventually, basically, you die, right, from some complication. It takes about a week in a lot of these cases. We do a case of people deliberately poisoning. There's a former KGB agent who was poisoned with polonium-236, 238 in London. That was it. It just looked at poison, and it takes like a week to kill him. But there's nothing you can do to stop it by and large, because the damage is everywhere. You can't remove any. There's nothing to remove. The damage is already done, and it's not like a toxin that you can take out, and there's not like an organ you can focus on. It's everywhere in the body at once. Very nasty stuff. The really severe blast they got at Hiroshima and Nagasaki, there are plenty of survivor reports, and there, you have to imagine, this is happening when no one has the slightest idea of what's going on. Of course, this all happened under tight secrecy, right? And so it was not just that, you have to realize, the firebombing of Tokyo killed as many people and destroyed 10 times as much property as the Hiroshima bomb did, okay? We have blown up Japanese cities before. It was nothing new. The difference was that one of the differences was the Hiroshima bomb was just a single bomb. There was one bomber, and then suddenly boom. And then also the stuff that came with it. In the days following the Hiroshima blast, when there were, and the people that were farther away from ground zero, that the hospitals and stuff were going in, they had people coming in, severe radiation damage. You know what else radiation does? It slices things up, right? You know what molecules will be susceptible to that? Ones that are very big and long will get sliced up. What are molecules that are very big and long? Fats, yeah, that's something I'm going for. These are, we work with what? Pretzels? Muscles. Muscle cells aren't that long. No, these are molecules, not cells. Not even talking about in your body so much, outside your body too. We use these all the time, what they call polymers, right? Polymers, these long things make plastics out of them, right? Long chain molecules get sliced up. Cable ties, the Swiss cable ties, when they're in the Tevatron, they break over time because they lose their stretchiness. The long chain polymers that make them up get sliced up. Well, you have polymers in your body too. They're used for connective tissue. They make things sticky. The radiation damage slices up the polymers and damages the stickiness of your connective tissue, which means that under severe radiation exposure, your body literally starts to fall apart. The parts that are stuck together lose their cohesion. And so there are actually stories from Hiroshima of people whose skin starts to fall off in pieces because of all the connective tissue being damaged. There's a story about someone, they said there's a story of someone holding their eyeball in their hand because it fell out. Okay? So there's a lot of it does a lot of damage to your body just from the radiation exposure, even if you escape the blast itself. And so the moral is nuclear weapons are very nasty. It is a blessing on us that it's only been used in war twice, and hopefully will stay that way. Though you never know these days. And so, the thing is, these things are really something. Now, this being wartime, we did not stop there. In fact, well before this design was even finished, Edward Teller, who taught this class for 2 weeks one time, did you know that? He taught at IMSA, modern physics, for 2 weeks as a guest lecturer because he's a friend of Dale Letterman's. Edward Teller came and started working on what they used to call the super. Here's what they worked at. You know how we talked about the mass of uranium, so mass of uranium-235 minus the mass of the fission products, oops, that says fission, right, is equal to about 0.25%, right, quarter of a percent. So they started looking at other things and said, what are other mass differences that work better? And you know what they found? The biggest difference is that 2 times mass of hydrogen is greater than 2 hydrogen atoms has substantially more mass than a helium atom. Turns out, right? We measure. Oh, let's look at that, right? Well, what does that mean? It means if you could take 2 hydrogen atoms and make them into a helium atom, what would happen to all that leftover mass? It would be released. And what's the factor here? It's about, it's closer to, it's about 2.5%, roughly. That's 10 times, that's right. Furthermore, unlike uranium, where do you find hydrogen? Everywhere. Specifically what? Where? What? Water. Water's a lot of hydrogen in it, right? You think about it? It's mostly hydrogen. So, and you can find water fairly easily. So they start working on the idea of taking 2 hydrogen atoms and pushing them together to make a helium atom. Now, how do you do that? It's not like ripping something. It's easy to imagine ripping an atom apart and that releasing a lot of energy. Here it's a little different. You have to take 2 atoms and push them together. Remember there's that big barrier that's called the...
Electric.
Well, the strong force that makes it work. Now, remember what it's called? The Coulomb blockade, right? That stops them from getting together. So, unlike the other ones, there's only one way to do this. It's to get it hot. If it's hot enough, the particles, you know, hot heat is random motion, right? The particles bounce around enough, they will smack into each other, and if they smack into each other hard enough, then they will overcome the electromagnetic repulsion, get into the strong force regime, form a new nucleus. The leftover energy will get released as heat. So, how hot does it have to be? Well, we know one place nearby that actually generates fusion naturally. What's that? The sun generates fusion naturally. Its power comes from fusing hydrogen into helium. So we know how hot it needs to be. How hot does it need to be? How hot is the center of the sun? Unfortunately, we had nothing that could reach that kind of temperature except a nuclear bomb. Remember? So they come up with the crazy idea of using one of these, actually several of these, to trigger a fusion reaction. So the way it works, the original design, the first design, the other ones are highly classified. This one's only partly classified. So the original design, which is less of a bomb and more of a building, you put a plutonium bomb up here. And up here you have water. I mean, up here you have water. Actually use heavy water, water made with deuterium. And then you line this part here with this very, very complicated 7 layers of different materials that very, very carefully calculated. In fact, the first use of the first digital computer, ENIAC, was for hydrogen bomb calculations. When this thing blows up, the first thing to come out are gamma rays. Okay, so before anything else happens, the gammas are here, right? Okay, this stuff is very specially designed that it absorbs the gammas and somehow and re-emits them backwards, so that it ends up with the gammas pushing this way. The energy of the gammas is so intense that the gamma rays are able to compress the water. They actually squeeze this water in. It's a shock wave made of gamma rays. It squeezes the water in, raising its temperature as it squeezes down, ideal gas law and all that, right? As it squeezes down, it increases its temperature higher and higher. In the middle of here, what they do is they put a little piece of plutonium that they call the spark plug. When the shock wave of this reaches plutonium, compresses that, causing it to explode because of plutonium, and it blows up, pushing outward, and in between the expanding shock wave here and the inward shock wave of the gamma rays, the water in here becomes so incredibly hot, it reaches the temperature of the center of the sun, the fusion temperature. You might be like, wait a minute, you basically blew up 2 plutonium bombs to do that. Why don't you just blow up 2 plutonium bombs? And if you ask that, it's because you don't understand the scale of the hydrogen bomb, often called thermonuclear bomb. Really a fusion bomb is the right word. This, of course, is called fusion, opposite of fission, right? Still a battle here. The scale of it is like this. The blast of the Hiroshima bomb was gigantic. So gigantic they had to invent a new unit. The unit they used was equivalent tons of TNT. Okay? If you imagine taking a ton of TNT and blowing it up, right? That's the yield of an explosion, right? That's the unit they use. Tons of TNT equivalent. Okay? The blast of Hiroshima bomb, which was this design, was 12 kilotons. Okay, so if you took 12,000 tons, right, so 24 million pounds of dynamite and blew it all up at once. That's the Hiroshima bomb. Okay, so that's big. All right, a mid-sized thermonuclear bomb has a blast of 1 megaton. 1 megaton, okay, 1 million tons of TNT, right? That's 2 billion pounds. Right, and that's a mid-sized hydrogen bomb. The fusion bomb is as much bigger than the fission bomb as the fission bomb is bigger than a conventional bomb. Okay, it is many orders of magnitude bigger. If something horrible happened and one of these were to be dropped in Chicago, it would blow up downtown Chicago, which would be bad. If one of these were to hit Chicago, it would blow up all of Chicago, and we'd be lucky to be in a bomb shelter out here. Except sadly, it's not even a bomb shelter because the ceilings are very thin, so it wouldn't even help us. All right. But at least we don't have to worry about glass shattering there, so there's no windows. So these things are these can still be considered as tactical weapons, meaning weapons that could be used in war. They haven't been. They could be used in war. These cannot be used in war. They can only be used. They cannot be used tactically, meaning as a battlefield strategy. They can only be used to destroy, like cities, islands, continents. In fact, there was an island called the Bikini Atoll. That's where the bikini comes from, and it's not there anymore. You can't visit it because we blew it up. Well, look, Pacific Islands are great places to do hydrogen bomb testing because no one's around, got a lot of water there to absorb everything. You just put naval vessels around to catch the stuff, to measure the blast and stuff like that. That one they misjudged. There was a fusion reaction they didn't know about. That they misjudged. They thought it was going to be 3 megatons. It ended up being 7. It was big, and there's no island there anymore. Yeah. The longest bomb in history is the Soviets NORAD buster, as they call it. You guys know what NORAD is? It's the North. I don't remember what the acronym stands for. It's basically our big emergency defense base. It's where you take the president in case of nuclear war. It's built underneath a mountain in the Rockies somewhere, because where else do you hide from a nuclear bomb but underneath the mountain? So it's tunneled underneath the mountain. The Russians are like, oh, well, in case of a war, we better take out that mountain. So they have these missiles that carry like 25 megaton warheads, and they would plan to send a few of them, I think, to basically take out the entire mountain. Because that's how it works. Obviously never been used. That's a good thing. The U.S. was never big on the size. We were always big on accuracy, always our strength, and so we had things like the MX missiles. The MX missiles are nuts. They have the most ridiculous accuracy. You shoot up a missile. It's an ICBM. You're shooting from like Arizona and aiming at Moscow, right? And it shoots, so that's around the Earth, right? So it flies around the Earth. Apparently, actually takes photographs of the stars and uses it to readjust its head. Yeah, it's pretty cool. And then they use that, and then at the top there, it splits into 10 warheads, each one 1 megaton. The 10 warheads will land in 10 different locations, and each one's a 1 megaton warhead, a small one, And they are so accurate that our accuracy is 5 out of the 10 will land within 75 feet of their target, okay, across the Earth. And we did that in the 70s, man. So like, what do we have now that's classified? I don't even want to know. So the fact is, the Cold War, you guys, and things like the Cuban Missile Crisis, the Cuban Missile Crisis, the head of Strategic Air Command, Robert McNamara, was telling Kennedy to do a preemptive strike. He believed that with a preemptive strike, probably correctly, that America had enough edge in the arms race that we could, as his famous term was, bomb them into the Stone Age and only lose maybe 2 or 3 U.S. cities. Fortunately for us, President Kennedy decided that losing even 2 or 3 U.S. cities was not an acceptable price to pay, and they did not launch any nuclear weapons. We have to understand the amount of nuclear weapons that was in the air or in missiles ready to go at the time of the Cuban Missile Crisis, like armed and ready to launch, they're always armed and ready to launch, was 1,000 megatons.
It's a lot
1,000 megatons of ordnance we could have dropped.
Almost enough to.
The amount of damage that would have done would have been more than Russia. We later realized with some more models that it would blow so much dust into the atmosphere, it would block out the sun, cause what they call a nuclear winter, kill those people on the planet. So, good job, Kennedy. And so, the point is, nuclear weapons are bad. You should stay away from them. Unless, by the way, on a little side note, someone has to maintain these things. You can't let them sit there. That's extremely dangerous. That's the worst thing you could do with a nuclear weapon, right? You have to maintain it very carefully. You don't just let them sit there and hope they go away, right? So because of that, one of the biggest job needs coming up right now is to work as a nuclear physicist in the DOE, the Department of Energy, which maintains a nuclear stockpile, because they're always short nuclear physicists because it's like such a bad name. Oh, no, nuclear, I don't want to do that. I want to save the Earth. Well, you want to save the Earth from nuclear destruction, keep our nuclear stockpile working, please. So it doesn't fall apart. That's not what we want. Right? So if anyone wants a good
Push
job,
the big red one. Nobody. It just exploded.
I'll see you guys tomorrow.
Oh my word, that's not even. Okay, we have enough bubbles to cover